discussion of organic molecules today with the last major group we're going to talk about called carboxylic acids. And this is a two-part lecture. We'll do the beginning, introducing carboxylic acids today, and the next time we'll talk about some derivatives of those carboxylic acids, what we can make from them. So today I want to remind you how we get to a carboxylic acid. So this chart is nothing new. We've seen it before, where we have the list of alcohols on the left, our primary, secondary, and tertiary alcohols. And to remind you, that means that the oxygen attached to a carbon, so the carbon that the O is attached to, is connected to either 1, 2, or 3 other carbons. All right, so you have primary, secondary, and tertiaries. The only exception to that was the methanol, which the carbon was connected to no other carbons, and we threw that in with primaries. So to remind you of the reactions that we do here, if we oxidize these alcohols, we get either aldehydes from a primary alcohol, ketones from a secondary alcohol, or no reaction at all from a tertiary alcohol. There is no hydrogen to lose here, so this cannot be oxidized, which limits our discussion to the top two at this point, primary and secondary. A primary alcohol oxidizes to an aldehyde, right, and a secondary to a ketone because it's not on the end of the chain. If it were on the end of the chain, it would be a primary alcohol. Additionally, the aldehyde can be oxidized one more time because there's another H here, right? Or there's still an H there. And it can be oxidized once more to something we call a carboxylic acid. Right? So in this case, we've made additional bonds between carbon and oxygen as we oxidize these, and we'll do that one more time here. Where did the other oxygen come from? It came from a water molecule. Right? So what's happening here is the hydrogen that's here is leaving, is being replaced by an OH from water. Okay, so the aldehyde here is making 2 bonds to oxygen, and now it's making 3 bonds to oxygens. Right, so we went from 1 bond between carbon and oxygen to 2 to 3 total bonds between carbon and oxygen. Same thing happened with the secondaries. We went from 1 bond in the secondary alcohol to 2 bonds in the ketone. Ketones cannot be further oxidized because there's no hydrogen to remove here. And same thing with tertiaries. We went from 1 bond to carbon and oxygen to that's it. You have no hydrogen to remove, so it cannot be oxidized. All right, so what we're going to talk about today is how we turn these aldehydes and primary alcohols too into carboxylic acids, doing this oxidation reaction, and the physical and chemical properties of these carboxylic acids. Okay, so let's look at a carboxylic acid and see how it gets its name. So at the top here, we're going to start with a simple alcohol, so 1-hexanol, which is just a straight chain, carbon chain, 6 carbons, and there's an OH group on the first carbon. So it's a 1-hexanol, and you know we changed the ending from hexane to hexanol to indicate that. Right? This is old news. If we oxidize this 1-hexanol to an aldehyde, we'll get hexanal. This carbon is now making 2 bonds to that oxygen. It's a carbonyl, right? And this was the highest thing on my priority list right now. And then if we take this aldehyde, which its name comes from the alcohol that's been dehydrogenated, that's another name for oxidized. We've removed hydrogen, dehydrogenated. That makes it an aldehyde. That's where it gets its name. If we do this one more time and oxidize it to a carboxylic acid, it's now going to have a carbonyl and a hydroxy group again. It's not an alcohol anymore. It does have a functional OH group, that's true, but it's not an alcohol because this carbon also has a double bonded O on it. So this is, as a group down here, called a carboxyl group, and it comes from a carbonyl and a hydroxyl on the same carbon. So that makes it a carboxyl group. They must be on the same carbon. They can't be separate places. And if you flip to your priority list, where we had at the top aldehydes and ketones from last time, we're going to add one more to the top of the list, and that's going to be carboxylic acids. And this will be the highest thing on your list all semester. So we've completed our list to the top. We're going to have to go back and add some in the middle, just a couple things in the middle later on. But carboxylic acids are going to be on the top of your list. It's the highest priority thing we're going to see. So go ahead and add that to the top. Right, so we went from a primary alcohol to an aldehyde to a carboxylic acid. These are steps of oxidation. If I were to go backwards and take a carboxylic acid and reduce it, I would get an aldehyde. And if I reduce it again, I get a primary alcohol. Okay, so let's look at some of these simple carboxylic acids. They're called monocarboxylic acids because they only have one carboxyl group. And so the simplest one there is methanoic acid. There's just a single carbon there. So one carbon with a carboxyl group, right? It is the carboxyl group, and the only other thing is a hydrogen there. That's as simple as it gets. So it's a one carbon carboxylic acid called methanoic acid. So the way we name these is we change the ending from methane, we drop the E like we've done with all the other things, and we add this oic acid ending. It's two words. The second word is simply acid, but it's two words now. This is the first name you've seen with two separate words. So methanoic, and then we just append the word acid after it. Right? If it had two carbons, it must be ethanoic acid. 6 carbons would be hexanoic acid, and so forth. So all you do is count the carbons. And much like aldehydes, since these are derived from aldehydes, you know the carbon has to be on the end of the chain. So for primary alcohols, for aldehydes, and for carboxylic acids, the carbon we're interested in is always at the end of the chain. So by definition, it will be number 1. So carboxylic acids, just like aldehydes, are always located on number 1. And so we don't have to tell you this is a 1-ethanoic acid or 1-propanoic acid. It's on number 1 automatically on the end. And therefore, this carbon must begin our longest carbon chain, much like with aldehydes. And of course, we have our benzenes that get their special names. We have some carboxylic acids that are on benzene rings. So the simplest one you can do is benzoic acid. You notice the carboxyl group can't be a member of the ring because there's no way we can put 3 bonds. This requires 3 bonds to oxygen. There's no way we can put 3 bonds to a carbon that's already in this ring and has 3 bonds already. You can't make 5 or more bonds to carbon. So this must be standing off of the ring, right? There's no extra carbon in between here. There's the 6 in the ring and there's the 1 here. Remember, lines are not carbons. Lines are just the bonds connecting atoms. So we have a benzoic acid. If I modify that by putting something on the benzene ring, like the one at the very bottom, this is called iodobenzoic acid. And I'm going to consider where the carboxyl group is attached as number 1. This one doesn't get a number this time because there's nothing you can add to it. There's nothing you can add to this position because all 4 bonds are already filled and required to be this benzoic acid. So I'm going to call this position 1. Again, you can't add anything there. And this is going to be number 2. Or this one would be number 2. And then these would be 3, and this one would be 4 if there was something attached there. So to put an iodine out here as an iodobenzoic acid, I need the 2 because it could have been on 3 or 4. Can't be on 1, obviously. You can also call it ortho, which means the same thing as having something on 1 and 2. So ortho can take the place of 2 because this is a benzene ring. Right? It can also be meta, it can be para, depending on its position. The one in the middle here is called toluic acid, right? Because I have a methyl group in a meta position here, so it's meta-toluic acid, and 1 and 3 in positions to the carboxyl group. You can also call this a 3-methyl benzoic acid if you want to, because it's on number 3. Right? So either way is fine with me. It's just another name for it. Right, so be familiar with how you name these carboxylic acids. It's fairly simple. You have to start with this carbon, count the longest continuous carbon chain. Those are the simple ones. And then we have this 1-benzene derivative, which is it's sitting off of the ring. Right? It's the only one that's going to look like this. Okay, so here's an example of a biological molecule where you're going to find carboxylic acids and many other features. So this is called biotin. It's one of our cofactors we need in carboxylation reactions in the body, which we'll talk about later. But this molecule has some features you've seen. Right? So what do you call this feature here at the top? What is this piece here?
Carbonyl.
It's a carbonyl, exactly. It's not a carboxylic acid. It's not necessarily a ketone or an aldehyde, but it's definitely a carbonyl. We have another one down here. This one is part of a carboxylic acid, but this is just called a carbonyl. We haven't gone over nitrogen yet, so I won't burden you with the names for these rings yet. But that is a carbonyl. What I wanted you to recognize. Excellent. What is this thing down here? This ring with a sulfur in it. Pretend it's an oxygen, and then change the name.
It's thiol.
It's a thiol, but it's not a thiol. It's more of a what? There's no H on it. If it were an H, it would be a thiol. But there's no H on it. It's more like a what? If this were an oxygen, what would you call it?
Ketone.
Not a ketone. Ketones are like this. They have carbonyl.
Oxy.
If it were an oxygen connected...
An ether?
An ether, exactly. But it's not an ether. It's a sulfur, so it's called a... Just change the name. Thioether. Okay, so it's like an ether, just with the sulfur. Like we had a thiol instead of an alcohol. So instead of an ether, it's a thioether. We just append this prefix thio to mean sulfur. Right? And it's in a ring, of course, so we'll call it a cyclic thioether. It's another functional part of this molecule that's required for it to work. And then on the end down here, what is this long group here? What do you call this thing?
Ketone?
It's not a ketone. It does have
Carboxylic acid?
It's a carboxylic acid, right. If it didn't have this OH on it and there were some other carbons over here, then it would be a ketone. But this is a carboxylic acid, is what we've learned today. So there's my long carboxylic acid. Go ahead.
I have a question. Just to reiterate, the only difference between the aldehyde and that is the OH on the end?
Right, it's been oxidized. So there's no H there anymore directly connected. It's an OH now.
Okay. Is that secondary, or was that like with primary alcohols, is that twice? Once it's oxidized twice, or just once?
Correct, it's twice. So you go from primary alcohol, oxidize once to an aldehyde, oxidize again to a carboxylic acid.
Okay, thank you.
Secondaries can only oxidize once to a ketone, and that's the end of the line. You can't oxidize it anymore. And of course, tertiaries can't be oxidized at all. Okay, so good.
I have a question.
Go ahead.
Where did you get thio or thio when you're naming, like, why is that the name that it gets from sulfur?
The sulfur prefix is just termed thio. Just like we call, bromo for bromine and fluoro for fluorine. Thio means sulfur.
Okay.
That's just the word for it.
Okay, thank you.
Okay, so here's a multiple choice question for you that you might see on an exam, very similar to this one. So I drew 6 molecules here, and I asked which of these contains a carboxyl group.
I'm sorry, I have a question.
Yes?
Can you go back on the last slide? I'm sorry. When you're talking about thioether, the ether is the 2 carbons, right, around the sulfur?
Correct. It's an
okay.
ROR arrangement, but instead of an O, it's an S. So if it were ROR, remember R just means some carbon chain, then it would be an ether. But instead of an ether, because it's a sulfur instead of oxygen, it's called a thioether. This thio prefix just means I'm a sulfur, not an oxygen.
Thank you.
Okay, so of these 6, which contain carboxyl groups?
Number 1.
Number 1 does, yes.
And number 6.
Number 4?
And number 4, you said?
Yes.
Number 6.
Yes, number 6 is correct. Number 4 is not. What's different about number 4? Why is it not a carboxyl group?
Not on the same carbon.
They're not on the same carbon. Right.
They are not different.
Right. So if you look at number 1 and 6, the carbon has 3 bonds to oxygen, 2 to this one and 1 to that one. Right. So it has a carbonyl on it and an OH on the same carbon. So does this one. All of the others don't have that. This one, they're on different carbons. Right. Just like number 4, they're on different carbons. And number 3 and 5 don't even have a carbonyl. Right. There's no double bonded O. Yes, it's got 3 bonds to oxygen, but that's not what you're looking for. You're looking for a carbonyl and an OH. So just because it's got 3 bonds is not the right answer. This is a triol, right? Just 3 OH groups attached. And this one is a what? What's number 5? What do you call that? Where it's got an OH and an OR on the same carbon.
Hemiacetal?
It's technically not a hemiacetal. It's a what?
Cyclic hemiacetal? Cyclic one?
It's not a hemiacetal because there are no H's on this carbon. It didn't begin life as an aldehyde. It started out as a ketone.
Oh.
So it's a hemiketal.
Oh, gotcha.
Right. But you got the right idea. It's in that category of hemis. I agree. So it's an OH and an OR a carbon, you just have to check that there's an H left here to call it a hemiacetal. But there is no H, so it's a hemiketal. Often in industry, though, they're grouped together and called hemiacetals and acetals, so I'm okay with that. You get the right idea. That's more important than getting the two names distinguished. But for this question, I'm interested in today, you recognizing numbers 1 and 6 as carboxylic acids, and the others are not. What's the highest priority functional group in number 2? What would give it its name?
The alcohol.
There's something higher than an alcohol in here.
Or the carbonyl.
A carbonyl.
Carbonyl.
So this would be a what in its name? Since
A ketone?
it would be a ketone, exactly. We can go about naming these if you want after class or some other time, because you've done these before, but it's a ketone is the highest group here. What about number 3, the highest priority thing?
The alcohol.
The alcohols, right? And there's 3 of them. Right, number 4, the highest priority thing?
Alcohol. Oh, carbonyl.
Not the alcohol, but the ketone. Right, the carbonyl making this a ketone. That's the highest priority. Remember, these are higher than alcohols because they have more bonds to oxygen. And that's why carboxylic acids are our highest yet. It has 3 bonds to oxygen here from a single carbon. Right? This has 3 separate groups on it. That's not the same. Right? And then number 5, the highest priority thing?
The alcohol.
This time it is the alcohol. Exactly. This time it is the alcohol. Ethers have no priority. They are grouped with everyone else. All right, so the alcohol is the highest priority here. Okay, good. Here's some examples where carboxylic acids are present in molecules you may be familiar with. Right, so these are non-steroidal anti-inflammatory drugs, or NSAIDs. They're often given for low-grade fevers, and they're not addictive generally, because they're non-steroidal. And so what these two molecules, naproxen and ibuprofen, have in common is a benzene ring in the middle, of course, but they also have this propionic acid, or propanoic acid. Right? So it's a 3-carbon carboxylic acid. And this is where I often see people get confused on finding these 3 carbons. Right? So find this 3-carbon propanoic acid in naproxen. Right? So this is obviously carbon number 1, and people usually get this one right, carbon number 2, but this is carbon number 3. This carbon is not in the propanoic acid. It's part of this ring. This bond is not a carbon. It's just a connection between the propanoic acid and the double ring structure. Right? This is not a carbon, it's a bond. Right? So this carbons 1, 2, 3 of propanoic acid are 1, 2, 3. Why is this one shown in such a weird way? We're not a straight line here. What is it indicating?
Is it going down, like in the plane,
Well,
running away?
Right, it's going away from us, behind the plane of the board here. Right? And if it were a solid wedge, it'd be coming towards us. But why is it shown that way?
Because of tetrahedral geometry.
Because it's tetrahedral, exactly. And what else can you tell me about this carbon? Beyond being tetrahedral, it has another property. We learned this last time.
Is it showing cis or trans?
It's not cis
It's
or
chiral.
trans, but you're close. It's not cis or trans, but it has another similar property.
It's chiral.
It's a chiral center, exactly. So it's chiral. There are 4 different things attached here. What are they? Well, we've got the methyl group down here. We've got this carboxyl group over here. We've got this big structure to the left, and there's still a hydrogen here not drawn, right? And it would be coming out towards us out of the board, right? You draw it as a wedge coming out of the board. Right? So there are 4 different things attached here that makes this a chiral center. And if you have a chiral center, that means there's 2 versions of this molecule. There's the right-handed and the left-handed version of naproxen. And only one of them is actually active as far as a non-steroidal anti-inflammatory drug. So when you're producing molecules like naproxen and ibuprofen, which has a very similar profile, right? They just differ on this end, right? With this chiral center, it means when you're manufacturing it, there are 2 options. And usually only one of the 2 is actually functional for the purpose you're making it. So you have to purify it from its counterpart, which makes it more difficult to do and thus more expensive as a drug. Right? Can you find any other chiral centers in these molecules? Like an ibuprofen, does it have another chiral center? Remember to check all of the tetrahedral carbons, so that would be this one, none of the ring are tetrahedral, this one is not tetrahedral, and these out here. This one has 2 hydrogens, these have 3 hydrogens each, and this one has 2 identical methyl groups on it. Right, so none of those are chiral. This is the only chiral center. So when you guys make this in lab, I think you're going to make ibuprofen, or maybe aspirin, depending what they choose this year. But you'll be making generally the pair of enantiomers. You'll make the 50-50 mix of this with the chiral center there.
I have a quick question. It's not alpha or beta because it's not in a ring, correct?
It's not alpha or beta because it's not a sugar.
Okay, gotcha.
So
So it's only for
right, sugars when they form into their ring forms or their hemiacetal or hemiketal forms, we call alpha or beta. But this is just the chiral center, right? It's either going to be D or L or E or Z or R or S or whatever system you want to use.
Okay, thanks.
Okay, let's build it a little larger. This time we have 2 carboxyl groups on the same molecule. This is nothing new. We've seen this before with alcohols. We've seen it with aldehydes, with ketones, with lots of substituents. With 2 chlorines, we call it dichloro. With 6 methyls, it'll be hexamethyl and so forth. You've done this before where you have multiple things. So when you have 2 carboxyl groups, since they are the highest priority thing, they must both be in the chain. So our chain is defined as going from one to the other, and it can't go anywhere else, right? It must directly go from one to the other. You can't take any offshoots and come back. So because they're both the highest priority, we must get them both in the chain, and that is always possible because you can go from one to the other. So our chain here is simply 2 carbons long. So it's ethane. We change the ending to oic acid because it's got a carboxyl group, but there are 2 of them. That means there's a dioic acid. Don't put the di in front of the ethane because there aren't 2 ethanes here. There aren't 2 pairs of carbons. It's just ethane. And it's got 2 oic acid functional groups. So ethane, dioic acid. This is just like when we did alcohols. If it were 2 alcohols, it would be ethane diol. Right? We didn't put the di in front of the whole thing. Right? So very simple combination here. If it's a little longer, it's propane dioic acid. Very simple. I need no numbers here because you know they're on the ends of the chain. They can't be anywhere else. Right? If I make it a little longer, 4 carbons, it's butane dioic acid. Right? Fairly simple. Right? Everybody okay with naming the dioic acids? Right? You don't have to memorize these other names. These are the common or the biochemistry names. We'll talk about these later. We'll actually use succinic acid later. But I want you to learn the IUPAC names for now. So 2, 3, and 4 carbons long dicarboxylic acids. Any questions on those so far? Because we're going to build on this. Okay. So let's start naming some of these carboxylic acids and put into practice the skills you have, the list of priorities, and the algorithm you use to find the longest chain and lowest number and add the substituents and so forth. So let's practice a few of these. So I'm going to give you 3 names here. You can ignore the common name here of formic acid. Just use the IUPAC name on top. Right? And I want you to try to draw these. So when you start at the beginning here on the first one, the first thing you always look at is the parent name. Right? So it's a butanoic acid. We'll deal with the jewelry later. Right? So let's draw a butanoic acid. How many carbons should you draw?
4.
4. And when you're drawing, whenever you put your pencil down to draw that first carbon, when you set your pen or pencil down, that's carbon 1. Remember, don't draw a line and call that number 1. You're already on number 2, right? Because they're at the ends of lines. So when you set your pen down, that's number 1. And you draw that first line, you're now at number 2, and then 3, and then 4. Okay? And then when you start drawing, keep in mind that when you call this number 1, and that number 2, and this number 4, you have to stick with that numbering scheme until you're finished drawing. So when you put your pen down and call it number 1, 2, 3, 4, or if you're going right to left or up top to bottom, it doesn't matter which direction you go. But if you draw 4 carbons and label them 1 through 4, it might help you in drawing it. Because you can't change your numbering system while you're drawing. Okay, so draw those 4 carbons, and then what does this butanoic acid tell me to do? Right, we'll deal with this stuff up here later. What does the oic acid ending tell me to do?
A double bond and then an oxygen on the first carbon.
Right, so on the carbon number 1, whichever you designated as number 1, you need to put a carbonyl, right, a double bonded O, and an OH on the same carbon. Be careful that you don't connect the carbon to the hydrogen, you connect it to the O of the OH. And if you have to write it HO instead, that's perfectly fine because you drew number 1 on the left, and there's nothing wrong with that. Right, that's what most people do. Right, and now we can go back and add on our substituents. So on number 3, put a methyl group, and on number 2, put a chloro, and you should get something like this. I chose the right as my number 1 instead of the left. You could have done it exactly the opposite. It wouldn't have made any difference. If you call this number 1, that would have been fine too. Right, but 1, 2, 3, 4, I put my carbonyl and the OH on carbon number 1. I put a chlorine on 2, and I put a methyl group on 3. And the next one's actually fairly simple. It's a fluoromethanoic acid. What's the longest chain here?
1.
1. So how do you draw that?
A dot.
Put a dot on your page, exactly. And on that dot, what should we do? It's a methanoic acid.
Double bond in the OH.
Yep, so a double bonded oxygen and the OH on the same carbon, the only carbon that's there. And then on that, we need to add one more thing,
Fluorine.
a fluorine. So I, again, put the OH to the right. You could have put it to the left. It doesn't make any difference as long as you write HO and not OH. Right? And then you could have put the fluorine over here. Right? But it's a 1-carbon chain. It's a carboxylic acid with a fluorine on it. And fluorine is F, not FL. FL is Florida. Right? And then the one on the right, we have a propane dioic acid. How many carbons in that?
3.
3. And it's a dioic acid. What do you do there?
2 carboxylic acid groups.
All right, exactly. We put 2 carboxyl groups. Where would they be? I didn't tell you. And that 2 out in front is not describing that at all.
It's on 1.
One of them's on number
It'll be
1.
on the ends of the chain.
They must be on the ends of the chain. So in this case, since it's 3 carbons long, one of them's on number 1, and the other's on number 3, because that's the other end. Okay, so you should draw 3 carbons. Right, 3 carbons long. 1, 2, 3. These are not carbons. So 1, 2, 3. I put carboxyl groups on each end, like that. And on number 2, I put 2 methyl groups, like it says. So on numbers 2 and 2, I put 2 methyl groups, 1 and 2. Right.
I have a question.
Uh-huh.
Would it matter if you drew the methyls as kind of like a straight line? You know how you see that sometimes?
As a straight, I did draw them as a straight line.
No, but you know how they're like facing each other? Would it matter if they were on like opposing sides of the main line?
Oh, you
know what I'm saying?
mean one on top and one on bottom?
Yes.
Yeah, that's perfectly fine. As long as you
Okay.
realize that that carbon in the middle is still tetrahedral, right? They're not exactly opposite one another when you do that.
Okay.
Right, just keep the geometry in mind. You could have drawn one up and one down, and I'm perfectly happy with that. But keep in mind that that central carbon is not a square or a cross like you see it. It's tetrahedral. Right, so it's often drawn.
And does it?
I'm sorry.
And does it matter if you were to put one O, like one of the double bonded O's on top and one on bottom?
No.
Are they supposed to be on
The only
sides?
reason they're both facing up is because that's the way the angles were drawn, right? And if you go back, you'll see that sometimes it's facing down when it was angled down.
Oh, okay.
That's just a convenience in drawing. You could have drawn this down and the OH up, and I'd be happy with that too, as long as the connections are correct.
Sorry.
Go ahead.
That first one, the 2-chloro-3-methyl butanoic acid, is that just because I was having trouble with chiral centers last time? Is that carbon where the chlorine is chiral?
Yes, it is. So carbon number 2 here is chiral because it has 4 different things attached. Yes.
Thank you.
And the one over here, number 2, is not chiral because there aren't different things attached. There's actually 2 of one thing and 2 of another attached here. Yeah, but good question. Right, does anyone have a problem with this third one's name? I mean, we drew it correctly from the name, but is there a problem with the name?
There's nowhere else the two methyl groups could be.
Right, those twos are unnecessary. Where else could they be? They can't be on number 1 or 3 because it's completely full with the carboxyl groups. So they couldn't have been drawn anywhere else. So they become superfluous. You don't need those twos. So dimethyl propane dioic acid perfectly gives away its name, or its drawing just fine. But some people will like you to keep the twos. Again, we're going to go with the minimalist approach. If we don't need them, we're not going to include them ever. Okay, so let's play the opposite game. I'm going to give you 3 structures, and you give me their names. Right, so just as easy to do. Find the longest continuous carbon chains, right, name them, and then add in the substituents. So on the first one, what's the highest priority things you see? So go down your priority list. What do you see? Carboxylic acid right here and right here. So these 2 carbons must be in the chain if possible. And it is possible. In fact, I can get all 3 carbons in the chain. Right? So if we begin and end at those groups, so it's 3 carbons long, we'll call it what?
Propane.
Propane. Change the ending.
Propane dioic, whatever.
Well, the second word is pretty easy. It's just acid.
Yeah.
So you're absolutely right. Propane dioic acid. And then one other thing to add to it.
2-fluoro.
Just like that, right? 2-fluoro
Yes.
propane dioic acid. Exactly what you said. Does anyone have any issue with this name?
Is the 2 necessary?
Is the 2 necessary? What do you think?
I think no.
No, it's not.
It's not, exactly. For the same reason. All right, but good. I would write it the way you did it as well. I would put the 2 on there to start and then go back and ask that question when I'm finished drawing and writing. Okay, good. How about the next one? So find the highest priority thing in this molecule. Carboxylic acid, right? There it is. This must be carbon number 1. Right? These, either one could have been number 1, but this one is the only one present, so it's number 1. So what's the longest chain that starts here?
Propane?
3.
3. So propane, exactly. So we change the ending to propanoic acid. Don't forget the second word. It's very easy second word. It's always going to be acid. So propanoic acid. And what else is on my propanoic acid? I have a couple things here. What are these things?
It's a dihydroxy.
Right, so these aren't alcohols anymore. It's going to behave like an alcohol in this part, but they're not called alcohols because they're not the highest priority game in town. That's a carboxylic acid. So they don't give it its name. They've been demoted to substituent status. So in this case, they're called hydroxys. It's a hydrogen attached through an oxygen, much like ethers. Right? And if you don't win, you're no trophies for second place. You become substituents. So it's a dihydroxy, right? Propanoic acid. And where are the hydroxys? They're on number 3, both of them. So it's a 3,3. That's their locations. Dihydroxy propanoic acid. So my question is, are the 3s necessary?
Yes.
Yes. Why?
They could be on 2.
It could have, one of them could have been on 2, or both of them could have been on 2, right? Exactly right. So other options exist that are not 3,3, therefore I need the 3,3. Whereas in the previous 2, no other options existed, so the numbers were unnecessary. All right, good. How about the last one? Highest priority thing in the molecule.
Carboxylic acid.
Carboxylic acid. Imagine that all day today. All right, but you're going to see some that aren't, of course. Carboxylic acid, and of course, what is the longest chain that must start at this carbon?
Methane.
1, right? You remember the rule, excellent, that you can't go outside to inside of a ring. This carbon's part of this ring. So you can't be in the ring and out and be in the same chain. So this is it, 1 carbon. I know this is longer, but this has priority. So priorities are what matter. So here, 1 carbon long, so what's its parent name going to be?
Methanoic acid.
Methanoic acid, very good. And what's attached to my methanoic acid? There's no carbon in here, keep that in mind. It's just a line. This thing is attached. So it's a cyclo, I agree. How many carbons?
5.
5, so it's a cyclo what?
Pentane.
Not pentane.
Pentox.
Right, not pentane, but pentyl. Remember, it's not the main chain. It's a substituent. So it's a cyclopentyl with the YL adjective ending. Right, so cyclopentyl methanoic acid. Right, the common name for methanoic acid is formic acid. That's why it says this here. But I want you to know this one. Okay, so cyclopentyl methanoic acid. Why are there no numbers here? How do I know where to put it?
It's automatically on number 1.
Yeah, because there's only 1 carbon to put it on, right? The methanoic acid only has 1 place to put it. So I don't need to say 1 here. So excellent. Okay. So let's look at a couple
I have a question real quick.
Go ahead.
So you only name the carboxyl group as part of the ring if it's a benzene ring?
Right, that was a special name for benzene ones because it was a benzoic acid. That's the only one like that.
Okay.
Right, it's the benzene rings have their own little game going on where they all get their own special names and such. But for the rest of these, it's not part of that ring if it's not in the ring. And carboxylic acids, like aldehydes, can't be in rings because they must be on the end of the chain. Okay. So for this part, we're going to start combining things, right? So you've practiced very well there. You got a lot of these names down. But this part is to remind you that if you're not the highest priority thing, you still must be included in the name, but you're generally a substituent or you've been downgraded, right? So in this case, we're going to try to incorporate all the parts in the name, and the words are going to sound kind of funny. They're going to get hard to pronounce because we're going to keep changing vowels and such, but that's just the way it works. That's the system we've decided upon. So in this slide, we have what are called unsaturated acids. And what that means is elsewhere in the molecule, there's a carbon-carbon multiple bond. So a carbon-carbon double bond or a carbon-carbon triple bond. I know there's already a carbon-oxygen double bond because there's a carbonyl in this carboxyl group. But I mean, in addition to that, there's some other site of unsaturation, like a double bond or a triple bond. Okay, so these are called unsaturated acids. So in the first example here, in propanoic acid, it's 1, 2, 3 carbons long. This is highest priority, so it's number 1, and then 2, 3. So propane we start with. But it's a carboxylic acid, so we call it propanoic acid. But I must somehow indicate that there's a double bond. Well, if you remember, we changed the alkanes to alkenes to do that. We make that A into an E, so that's what I've done here. So it's propanoic acid, not propanoic acid. And this E tells me there's a double bond. So when you're writing these answers on your exam, don't make it ambiguous whether it's an A or an E there, because if I can't clearly tell, it's wrong. Right? So make sure you write your letters clearly, A or E there, or Y if it's a triple bond like this one over here. So right, and leave a space here if there's a space in the word. Right? So there's 2 separate words. So how do I know that the double bond is at this position? I didn't give a number here. I just said propanoic acid.
It can't be anywhere else.
Right. The only other option would be on between 1 and 2, and you know you can't add anything else here. It already has 4 bonds. So this was the only place it could possibly be realistically, so we don't need the number. Excellent. This is also called acrylic acids. This is what's found in acrylic glues and superglues, and superglue is effectively what they use for suturing now as well. It's just a different appendage on this thing. If you look in your slides, you'll see that at the end of your slide set. Right? How about the one on the right? So this one again has 1, 2, 3 carbons. Don't skip over this carbon. There is a carbon there. Why didn't I draw it at an angle? Because it's at the appropriate angle. It's 180 degrees. It's a triple bond. That's physically how it looks. So it's 1, 2, 3 carbons, and it's called propanoic acid with a Y, because that's a triple bond. Again, I don't need to give a number because the only place it could be is here. Okay, so similar thing, a double bond or a triple bond, in addition to the carboxyl group. Right? This one at the bottom, right, both of these at the bottom have 4 carbons in their main chain, so 1, 2, 3, 4, or 1, 2, 3, 4. So they're both butanes, They are both dicarboxylic acids. Right? You see that like we had before, right? So they have two carboxyl groups, so dioic acid. So they're both reading butane dioic acid, and they have double bonds on them. Right? The double bond is on number 2, so this 2 is sort of unnecessary, right? Because of where else could it be? But there is a difference in them. This one is cis, and this one is trans. How can they be cis or trans? Because there's differences on this side of the double bond, as well as differences on this side. We don't compare side to side. This side also has differences, and this side has differences. This one is cis because if you follow the main chain, it ends up on the same side of the double bond, north of the double bond here. If you follow the main chain here, it crossed the double bond. So if you have your imaginary line down the bond, it went from one side to the other. Here it stayed on the top of that imaginary line. So this one would be cis butane dioic acid or trans butane dioic acid. People often leave the 2 in there like before, or you can be the minimalist that I am and not put the 2, but some people don't like that.
Question.
Huh?
How are you seeing the differences? Are you talking about the differences in the H?
Yes, so the differences on each side mean this carbon has 4 bonds. 2 of them are to the other carbon that's forming a double bond with. That leaves 2 more bonds, one to this thing and one to a hydrogen that's not drawn. Those are different things from each other, right? As opposed to the one above it. Let's try that one. This one, we had the carboxyl group and a hydrogen. Yes, those are different. But this side have H and H. There's 2 hydrogens on this side. So they're not different from one another. This can't be cis or trans. But you must find differences on each side, and these qualify for that. Okay, here's some more. And this time, instead of adding a double bond or a triple bond to it, these are not called unsaturated acids, they're called hydroxy acids. Because they still have our carboxylic acid group, that's why they're called acids, but it has another functional group, a hydroxy, an OH this time. So instead of a multiple bond like we saw on the previous slide, we've got an OH. So here's a simple one with 2 carbons, right? Here's a carboxyl group, and on carbon number 2 I have an OH. What would the name of this be, the IUPAC name? We call it glycolic acid in biochemistry, but what would the IUPAC name of this be?
Two hydroxyethanoic acid.
2-hydroxyethanoic acid. Okay. Could you simplify it a little? Leave out something that may not be necessary?
Just hydroxyethanoic acid.
Hydroxyethanoic acid. Very good. You don't need the 2 because where else would it be? Okay, good. And you can find this glycolic acid in things like sugarcane or sugar beets or pineapples, melons, and white grapes. It gives them their tartness, right? So this is found in these plants. And underneath we have one that's very similar to glycolic acid. The only difference between glycolic acid and lactic acid is 1 more carbon. That's this extra carbon that this one did not have. That's the only difference. It gives it a completely different flavor profile, right? So you have a receptor for this on your tongue, and you have a different receptor for this one. So it's this methyl group makes a big difference. So it's instead of being 2 carbons long, it's 3 carbons long. We call it lactic acid. It's found in sour milk and sauerkraut and sour pickles. Right? It gives it that sour flavor instead of the tartness. Right? So what's the IUPAC name for lactic acid?
Oh shoot, I had it. Propionic acid.
So propanoic acid, 1, 2, 3. Yes, that's the parent name. And then you need to describe the substituent. Yep, you got it.
2-hydroxy.
2-hydroxy propane acid.
That's right. So
Propionic acid.
2-hydroxy propanoic acid, like propane, but drop the E and add oic acid. So 2-hydroxy propanoic acid. Excellent. Now, do I need the 2 for the hydroxy?
Yes.
Why?
It could be on 3.
It could have been on 3, exactly. So there's another valid option, so I need the number. There were no other valid options for this one. Okay, so let's go a little larger than these simple hydroxy acids. Let's make it a little larger. So this one's a dicarboxylic acid with a hydroxy. Right, so this is getting quite complicated. A lot of oxygens in this thing. Do you think malic acid here is soluble in water?
Yes.
Very soluble in water. In fact, all of these are. With all these O's, it's going to be quite soluble. Right? So hydroxy acids are almost always soluble, and it's what gives us a lot of our flavors in these plants. So this one's malic acid. It's what gives apples their flavor. This is what you think of when you think of an apple flavor. It's not the only molecule involved, but it's the main one. And so what would malic acid's IUPAC name be? So let's build it together. What would the parent name be? The ending.
Butane.
Butane, and then we change the ending to?
Butanoic acid.
Almost. There's two of them.
Butadionic acid.
Don't drop any syllables. I see that all the time. It's butane dioic acid.
Okay.
Right? We just don't drop the E this time to make it pronounceable. So butane dioic acid, yes. And there's one other thing on it.
Hydroxy.
There's a hydroxy, and where is it?
On 2 and 1.
It's on 2. Right?
2. Yeah,
Right.
sorry.
These are not hydroxys. Remember, these are part of the carboxyl groups. Right, so it's on 2. So it'd be a 2-hydroxy butane dioic acid. Anybody want to make a modification?
Is it dihydroxy?
Right. So 2-hydroxy butane dioic acid. There aren't 2 hydroxys. There's only one. These are not hydroxys. These are part of the carboxyl groups. They're included in the name. So anybody want to change the name?
Is the 2 unnecessary? Because it would be 2 either way.
Yes, the 2 is unnecessary. If it were on this one, it would still be on 2, because then this would be number 1. Because you have carboxyl groups on either end can be number 1. So either position here is called 2 if there's something on it. Right now, if you had one on here and here, like the one below, now they're on 2 and 3, or 2 and 3. Right? And this is called tartaric acid. So its name would be very similar to malic acid, but tastes quite different. Right? So this one, instead of being a 2-hydroxy butane dioic acid, this one's a 2,3-dihydroxy butane dioic acid. Right? And this,
Do we only have to know the IUPAC names, or do we have to remember these malic acid names?
we're going to learn the IUPAC names for now, because this is just an exercise in naming. But we're going to learn these later. Malic acid we'll use later. We won't see tartaric acid too much later, but malic acid definitely later when we do citric acid cycle. Right? But for now, I want you to be able to recognize this and name it with the IUPAC system. You don't have to memorize these now. This is kind of for your entertainment of what they're found in. Right? So this one has one extra OH group, and it gives the flavor of tartar sauce and the tartness of our dark grapes. Right? And this is the major component in our red wines. They give it its pH balance, right? The tartaric acid. Right, so let's do one more. This time I have 3 carboxyl groups on the same molecule. Right? It's technically impossible to get all 3 of them in the main chain, because you must go from one end to the other. You can't go from one to the other and then back down. So if you have 3 carboxyl groups, it would be impossible for you to name this with what you know right now. Right, so I won't ask you to name this one. It's actually citric acid, as we'll see much later. It's very important. It's found in citrus fruits like lemons and limes and oranges, and it gives them their very tartness. Right? But you should be able to recognize it as a hydroxy acid because it's got 3 carboxyl groups. Those are the main priority things, but there's still an OH on it. Okay. So I won't ask you to name citric acid because you haven't learned how to do that yet. But if you have 2 or fewer carboxyl groups, you can do it right now.
I have a question.
Okay.
So it's 3 carboxyl groups, right?
Yes.
So when you say carboxylic acid, are you talking about the whole citric acid?
Correct. It's a carboxylic acid as a molecule category. It just has 3 carboxyl groups that give it that privilege of being a carboxylic acid.
Okay.
Right? If you only had 1, it would still be a carboxylic acid. It just happens to have 3. Just like if you only had 1 OH, it would be an alcohol. If the only thing in the molecule was an OH, right? A carbon chain with an OH on it, it's an alcohol. But if it had two of them, it's still an alcohol. It just happens to be a diol. It happens to have two hydroxy groups. That's all this means. All right, and then lastly, we have our keto acids. So here we have our carboxyl group again as our highest priority, and then some other functional group that we've seen before, which used to be our highest priority before we learned about this one. It is no longer the highest priority. It's been demoted. So we have to name it somehow. You've learned to name these as hydroxys when they're not the main highest priority thing. How do you name this? Well, it's fairly easy. You just call it oxo because it's just an oxygen. So these keto groups, whether it's an aldehyde or a ketone, both are lower priority than a carboxyl group. And we just named them oxo groups, OXO, because that's all it is an oxygen attached. Right? But when you say oxo, I know it's double bonded attached. Okay, so in the name for pyruvic acid here, or pyruvate, which we'll see again later, as well as this one later at the end of the semester in our biochemistry. But let's name this one as far as the IUPAC name. So highest priority thing is the carboxyl group. So this is number 1. So what's the parent name start out as?
Propane.
Propane, exactly. 3 carbons. So 1, 2, 3. But it's not just propane. Let's change the ending. Propanoic acid, good. And on the propanoic acid, what do I have? An oxo group, right? So OXO, right? And where would it be located?
On 2.
On 2. So I have a 2-oxo propanoic acid. Do I need the 2?
No.
Yes, I do.
Yes.
Why?
I thought it would make the chain longer, wouldn't it, though?
If you put it on number 3, I'm only adding an oxygen, not a carbon. It doesn't make the chain any longer. But it would be a different molecule, right? It would actually be an aldehyde on the end, but that's still not a highest priority thing. It's still been demoted to being called an oxo group. So whether it's on 2 or 3, I still have to call it an oxo group because this thing has the highest priority. So I do need the number 2 to indicate where this oxo thing is. If it were on number 3, it would be a 3-oxo, right? Propanoic acid. So I do need the 2 there. So it'd be called a 2-oxo propanoic acid. Okay.
And that's one word, correct? Oxopropanoic.
2-oxopropanoic is the first word. No spaces in there at all, right? And then a space and then the word acid. Right? And that's the only spaces we've seen in everything we've named so far. It's just this second word called acid. Well, when we get to esters next time, we'll have some words with more complicated words in them, or names with more complicated words.
I have a question.
Uh-huh.
Oxo, is it OXYL? That's what you mean?
The
spelling.
It's just OXO.
OXO, okay, thank you.
Just like chloro or bromo or fluoro or iodo, it's oxo, OXO. Because it's just the only atom there. It just happens to have double bonds.
If that wasn't a double bond, what would it be called again?
Well, if it didn't have a double bond here, then the oxygen would have something bonded on the other side. Right? It can't just be a single bond to an O. The O needs a second bond. So if there's something on the other side, it happens to be an H, it would be a hydroxy. If it happens to be a methyl, it'd be a methoxy. If it were something longer, it'd be a something longer oxy. Right? It would be an ether. But because it's double bonded, it can't have any other bonds, so we just call it oxo. All right, good. How about the one on the right here? This is oxaloacetate or oxaloacetic acid. That's the biochemistry name for it. We'll learn about it later as well. But give me the IUPAC name of this one. Find the longest continuous chain that includes the highest priority carbons.
Butanoic acid?
So it's 1, 2, 3, 4. I agree. It's 4 carbons. These are the highest priority carboxyl groups. But there are 2 of them. So not just butane, but
Butanoic acid.
Butane dioic acid, right? We leave the E on to make it pronounceable. So butane dioic acid. And what else is in there?
An oxo.
An oxo. And where is it?
2.
It's on 2. So what would be the name?
2-oxo butane dioic acid.
Right. Is the 2 necessary?
Yes.
Where else would it be?
3.
Could it be on 3?
No, it can't.
No. If it were on the other carbon, it would be on number 2 from the other end. Keep in mind, when you have the dioic acids, either end could be number 1, much like we did back here with the malic acid. Right? Either end could be number 1, so it was on 2 automatically. Right? So here we don't need the 2, it's just oxobutane dioic acid. Right, so enough with the naming of those for now. You can practice lots of them later. But carboxylic acids were the highest in our priority list, and they're also going to be the most polar molecules we've seen. Right? They're going to be very high interaction with each other and with water. So if you look at your typical carboxyl group here, on the left, I have it drawn as a carbon in the center with some R group over here, doesn't matter what it is. And then I have my carboxylic acid group, so the double bonded O and the OH. I drew the OH bond out for you because you know it's not just an OH as one thing, it's an O bonded to an H. So I have this double bonded O here. You know there are 2 lone pairs on the oxygen if you draw its Lewis structure. Right? Don't forget about having those things. And this oxygen here also has 2 lone pairs and a hydrogen stuck to it. If I take another copy of that carboxyl group over here, because they're in solution together, right? There's 2 of them interacting. And they can interact in this way. It's called a dimerization or a bidentate arrangement. So bidentate means 2 teeth, right? So they have this interaction where the lone pair of one of the oxygens interacts with the H of the OH, and similarly the lone pair of this oxygen, one of them, interacts with the H of this OH. So one pair of molecules can make a 2-handed grasp of the other molecule. It's not just a single hydrogen bond here. Remember, hydrogen bonds are just attractions. They're not real bonds, right? They're not actual covalent bonds. So, but in this case, if I put 2 carboxyl groups next to each other and they face one another like this, they can hold on with both hands. So this is a much stronger interaction than if you only had, say, an alcohol or a ketone or an aldehyde or something else that could make one hydrogen bond with a water molecule or something else. So what are the consequences of this? That it can make these 2-handed grasps instead of just one. That means they hold on to each other much more tightly. So would it be more difficult or easier to pull one out of the solution, to boil it away?
More difficult?
What does that mean physically, if it's more difficult to pull one away from another?
It has a higher boiling point?
It has a higher boiling and melting point, right? Same thing with the solid. So a higher boiling and melting points than anything else we've seen for an equivalent mass. Right? So obviously if R gets longer, the boiling points go up. But the more carboxyl groups I put on it, the much higher the boiling point gets. Okay, so if you can imagine, what do you think the boiling point of citric acid might be? It's fairly high, right? Way higher than you'd expect it to be if it didn't have these 3 groups. Okay. All right, one reaction I want you to know with the benzenes, because we have to talk about them. So the benzenes have a reaction they do with an oxidizing agent. The benzene ring cannot be oxidized in and of itself. But if you have any R group attached to the benzene ring, so we have 2 carbons here, we have 3 carbons here, and quite a few carbons here, whatever the length of this chain is, it doesn't matter. As long as there's a chain on it, right, and then you oxidize it, you will always make benzoic acid. So all these other carbons, this 1 carbon here, 2 carbons here, and all these carbons here except that one, leave. They're just knocked off of this thing. They're displaced. And in its place is put this triple, or this 3 bonds to oxygen. So you always make a benzoic acid. If you take any kind of benzene ring with an alkene attached to it, right, and you oxidize it, you'll get a benzoic acid. And of course the other piece flies away. Right? So it's a very easy one to remember. If you have a benzene ring with an alkene substituent, right, just plain old carbon sticking out, nothing else, then if you oxidize it, you'll always get benzoic acid. This is how we make benzoic acid. So fairly easy reaction to remember. Right? And then the last thing we'll talk about is the fact that carboxylic acids, we've been calling them acids. What does that mean? Well, if something is an acid, it means it can lose a proton. Right? So you've talked about this with hydrochloric acid before, probably last semester, or sulfuric acid, or any of the others. But these are carboxylic acids that can do the same thing. They're not nearly as strong as those 7 strong acids you memorized, but they're called weak acids, but they do act as an acid. They can lose their proton. So here my ethanoic acid, right, or carboxylic acid here, is going to lose this hydrogen. Right? This H is not going to leave as a whole ion or as a whole atom. Just the proton is leaving. It's leaving its electrons that it's sharing with the oxygen behind. So remember, this hydrogen only has 2 electrons around it, and it's sharing both of them with the oxygen. There are no lone pairs on this thing. So when the H leaves as a proton, just H plus, right, and it attaches itself to a water molecule, of course, because it doesn't want to be by itself, so it sticks onto this O, forming hydronium. That's a coordinate covalent bond. What's left behind is an O. Instead of having 2 lone pairs, it now has 3 lone pairs, so it has a negative charge. Right, so this is called the conjugate base of this acid. You guys did that last semester, right? An acid plus what's acting as a base, the water's acting as a base here, forms a conjugate base and the conjugate acid. And all we're doing is transferring a proton from the acid to the base. And you end up with a separation of charge. So neither of these were charged before, and because I'm sending a positive charged proton here and nothing else with it, this is going to gain a positive charge. There it is. It's called a hydronium ion in water. And this is going to be called the conjugate base, or the carboxylate. So instead of being a carboxylic acid, it's called the carboxylate. So ethanoic acid becomes ethanoate. We've lost the term acid because it's no longer an acid, and we have the conjugate base form, which is O8. So we drop that oic acid ending, the one we just put on, right? In its place, we write O8. And you did this last semester as well. When you had acids and they lost their protons, they took on the names of 8. Right, so hydrochloric acid, when it lost its proton, you had chlorides. When you were done, instead of chlorine, we changed the ending. So same type of thing. We changed the ending from oic acid to O8. So it's called a carboxylate now. Right, and all carboxylic acids do this. Some to more to a degree than others, but they all do it. So you'll lose the H, become O minus, and that's called the ethanoate now. And this is going to be important for next time when we talk about esters, because it's almost the same reaction. Right? If you react them with these carboxylic acids with a strong base, like sodium hydroxide, and you remember this from last time, or from last semester, if you react an acid and a base, you always get the same 2 products. What are they? Acid plus base always gives you what 2 products?
Water.
Water and
A salt.
a salt, exactly. So it's the leftover pieces from the things. So in this case, our acid has lost its proton and become a carboxylate version with a negative charge. And the base here is losing its OH, right? And the H and the OH come together to make water. But the sodium left over is going to have a positive charge because the electrons go with the OH. And so the sodium and the carboxylate are attracted to each other. This is an ionic bond. And if you dehydrate it and remove all the water, it'll make a salt. Right? So it's called a salt and a water. So if I react a carboxylic acid with a strong base like sodium hydroxide, I will always get the sodium carboxylate. Right? So here's the positive thing listed first, sodium carboxylate, like most salts, like sodium chloride. But it's not chloride in this case, it's a carboxylate. So in this case, ethanoate or propanoate or benzoate or whatever it might be, but it ends in that O8 ending, plus water.